Okay, let's go ahead and get started. So let me just kick off by, as always, thanking everybody for taking a little bit of time out of your day to hear about some awesome science going on with Green Bank Observatory and the Green Bank Telescope. I'm Karen O'Neill. I'm the director of Green Bank Observatory. And so today we're going to have a quick overview by me, just talking about what's going on, some of the news on site and what's been happening around the site. And then after that, we're going to have a great science talk by Trey Wenger talking about the Galactic HII region and structures within the Milky Way galaxy. So let me go ahead and tell you a little bit about what's going on with Green Bank Observatory. So the current status of the observatory, like much of the US, things are getting better and better in terms of COVID. There are actually no new cases in the county, which you can see circled there, which is fantastic news. And the state of West Virginia, there's currently less than 2% of all COVID tests are positive, and that rate has been on a steady decline lately. The number of vaccinated people in the state is slowly rising, not as rapidly as we would all hope, but at least it's continuing to go up, which is good news for us. Looking on the site, we're off returning to work right now. We've got about 95% of our staff are fully vaccinated. And the big news for us is the staff can now come into work. They can work within their offices, which is great. Health checks are still in place, of course, and full operations on site. So the telescope is in full operations, but the site itself will resume on September the 1st. This gives people time to readjust after a long time from working from home, get their offices set back up again, and get used to the idea of working not in your pajamas for the full day. So that's the idea there. On site, as I mentioned already, the GBT is a 24 hours, 7-day operation. We're in the middle of summer maintenance right now. So this means the telescope is being painted. We've got our triennial inspections going on, and then just general repairs. We do a lot of our repairs, particularly to the actuator motors and things like that. Science Center has been open for outdoor lectures and walking tours for a while now, but our big news that's going on our site is that the Science Center is going to return to full operation soon. That is, people will be able to come, visitors will be able to take bus tours, go to the exhibit hall, and all of those fantastic things that we love seeing people. We love getting to tell people about astronomy, and we're very excited for the full operations of this, hopefully very, very soon. So if you're interested in coming to visit, watch our website. We'll be announcing it out. We'll be announcing it on Twitter and Facebook and everywhere else. We're very excited about the idea of moving to full operations with that. All right, a couple things coming up at the observatory. So of course, our community Zooms are continuing through the summer, and hopefully as long as people are interested. And so the next community Zoom will be on July the 7th on some radar observations of NEOs by Marina Brozovic. And then on July 21st, we've got a great talk by Jamie Pinata on the ion neutral connection and dense cores. The other big news coming out on site is that the opening for the single dish school will happen in about a week and a half. So on July the 1st, the single dish school we've decided will be hybrid. So that is, we will allow in-person attendance at the single dish school, and we would love to have anybody who can make it attend in person, but understanding fully that the COVID situation around the world is not stable and travel plans are not easy right now. We will have a remote option. So that means you'll be able to do call into all of the meetings hopefully via Zoom, and take part in observing sessions, remote observing sessions and all of that. So that sign up will be open. We will be asking people to give us their best. Starting face-to-face again and starting to interact with our observers. So with that, I would just like to thank you guys for coming again and hand this off to Trey to hear about his gears talk. Thank you.
Thanks, Karen. Yeah, and thanks to all the GBO staff for the invitation to come talk at the community Zoom today. This is pretty exciting. It's nice to see some familiar faces, even if just virtually. For those who don't know me, my name is Trey Wenger. I'm a postdoc at the Dominion Radio Astrophysical Observatory in sunny British Columbia, Penticton, British Columbia. It's about 4 hours east of Vancouver. It's a balmy 33 degrees Celsius right now, even though it's only 10 o'clock in the morning. But it's a beautiful place nonetheless. Here's in my background of this title slide is a picture of the observatory, which I haven't been to since March of last year. Still working from home. Hopefully I'll get back there soon. Just like to point out that I'm finishing up my last year of my postdoc. I'll be on the job market starting next year. So if this science interests you and you have some funding and like to hire me, please get in touch. All right, so my research broadly focuses on the structure of the Milky Way galaxy. When I talk about the structure of the Milky Way, I'm really talking about three different types of structure. Kinematic structure, how is stuff moving in the galaxy? You know, what does the galactic rotation field look like? Metallicity structure, that's like what's the chemical structure of the galaxy? What's the distribution of heavy elements across the Milky Way? And what can that tell us about galactic chemodynamical evolution and the history of star formation in the Milky Way? And the last type of structure is the morphological structure. You know, is the Milky Way a grand design spiral galaxy? If so, you know, what do those spirals look like? And where is the sun in relation to these spirals? And what can that tell us about spiral structure in general, and then also just the formation and history of the Milky Way? Of course, we have a unique perspective of the galaxy being stuck within it. That makes it quite difficult to kind of untangle these structures because, for one, you have to peer through the dust of the galaxy. But then also, even if you can peer through the dust of the galaxy, there's just a bunch of stuff along the line of sight that makes it difficult to disentangle the structure. You know, what you'd like to do is to fly out of the Milky Way and get a perspective upon it. You know, like this is a picture of the Whirlpool galaxy, where you can, you know, directly see the structure of this galaxy. Of course, we can't do that in the Milky Way, so we need a proxy, we need a tracer, we need a tool that we can use to kind of map out the structure of our galaxy. So there's many different tracers and proxies that you could use. I use HII regions. These are the ionized gas clouds that surround recently formed massive stars, OB-type stars. In this image of the Whirlpool galaxy, you can see all of the HII regions because they've used an H-alpha filter in red here that highlight all of the ionized gas coming from these nebulae. So why do we use HII regions? Well, the most important thing is that they're bright. They're particularly bright at radio wavelengths, where the thermal continuum emission is among the brightest sources of emission in the sky at about 10 gigahertz or so. And since it's radio wavelengths, you can peer through the dust. And so it's really easy to spot these HII regions using sensitive radio telescopes like the GPT. Second most important thing is that there's a unique spectroscopic fingerprint of an HII region, namely the recombination lines. If you see a recombination line, which is telling you that you're seeing some ionized gas, and therefore you must be seeing an ionized gas cloud, that's an HII region. So if you can find a nebulae and then discover a recombination line towards it, you basically, you know, proven to yourself that it's an HII region. You could derive some interesting physical properties of HII regions using the spectroscopic tracers, you know, either optical, you know, collisionally excited lines or the recombination lines. You can derive things like electron temperatures, chemical abundances, the metallicities. Specifically, these are zero-age metallicities, which means, you know, that since HII regions are young, you're getting a snapshot of the enrichment of that part of the galaxy today, as opposed to, you know, if you try to use stars as your tracer of galactic chemical structure, that's a little bit more difficult to interpret because stars are old, they've, you know, an unknown age typically, and they also, you know, radially migrate. So wherever the star is today is almost certainly not where it was when it was born. And so it really convolutes your interpretation of the present day galactic chemical structure. And then finally, you can get distances to HII regions pretty easily. So if there's a bright maser associated with the star forming region, you can use very long baseline interferometry to get a trigonometric distance, a parallax distance. But for most HII regions, there isn't a maser. And so for those, we rely on kinematic distances, basically assuming a rotation model of the galaxy and inferring a distance based off of the observed radial motion. So HII regions are great tracers of galactic structure. You can just kind of see directly in this picture of the Whirlpool galaxy that most, if not all, of the HII regions are associated with the dust lanes and the spirals of the spiral arms of the galaxy. And so the idea is pretty straightforward. If we can find all of the Milky Way's HII regions, maybe we can map out something like the structure of the spiral structure of the Milky Way. So this is what we were thinking about in about 2010. We were thinking maybe we should go out and find all of the Milky Way's HII regions. Here's what's called a longitude velocity diagram. On the y-axis here is galactic longitude. This is just position on the sky relative to the Milky Way. And on the x-axis here is the line of sight velocity and the local standard of rest frame. And all the black points here are the HII regions that were known prior to about 2010. At that point, there were about 1,000 H2 regions known in the Milky Way. It was clear at that time that we were missing most of the Milky Way's H2 regions. If you compare the census to another Milky Way-like galaxy, where we can count up the H2 regions because we can see them all, we know that there's many thousands of H2 regions in those galaxies, and so there's probably many thousands of H2 regions in the Milky Way galaxy as well. Second, there's different parts of this LV diagram that correspond to different regions of the Milky Way. So for example, in the first quadrant, which is between longitudes of 0 and 90 degrees, at negative velocities, so kind of here in this little rectangle of the diagram, this is a part of the Milky Way that's far away. It's on the other side of the galactic center in the first quadrant. And you can see that there's just not many points there. There's not many H2 regions that were known in that part of the galaxy at this time. And that's probably just because they were far away and faint. And so we knew that we had some more H2 regions to find, and that was the motivation for what we called the H2 Region Discovery Survey. This was a Green Bank telescope. Originally, it was a Green Bank telescope survey, and then we followed it up with some more observations from Arecibo. And the goal here was to search for radio recombination line emission towards infrared identified H2 region candidates. So we went to all sky infrared surveys like those done by the WISE and Spitzer space telescopes. We looked for nebulae that had the infrared characteristics of an H2 region, and then we went to these ultra-sensitive radio telescopes to search for the radio recombination line emission. So here's an example radio recombination line spectrum from the Green Bank telescope. This is the hydrogen recombination line. There's a little helium recombination line right next to it. And for this source, we did not detect a carbon recombination line. So just as a reminder, this is the spectroscopic fingerprint of an H2 region. So if it looks like an H2 region in the infrared and we detect this ionized gas spectroscopic tracer towards it, we're pretty confident that the thing that we're looking at is an H2 region. And the experiment was wildly successful. So we identified about 1,000 H2 region candidates that we observed, and we had a detection rate of about 95% for the radio recombination line. So it was a really fun experiment to go out and find all of these new H2 regions. The project took about 10 years, hundreds of hours on both telescopes. We typically observed at X-band, which is 8 to 10 gigahertz. And there with the old GBT spectrometer, we could observe 7 radio recombination line transitions simultaneously. And by averaging those together, you could really bump up the sensitivity quite a bit. And so over those 10 years, we discovered about 1,000 new galactic H2 regions. That more than doubles the number of known H2 regions in the Milky Way. And here on the right is the longitude velocity diagram, now showing in magenta all of the newly discovered GBT and Arecibo HRDS discovered nebulae. You can see how much we filled in this diagram, especially here in that part of the galaxy that I pointed out earlier. This is the distant first quadrant on the other side of the galactic center, and you can see just how many more points that we discovered there in this really far reaches of the galaxy. So this is exciting, and you're kind of getting close to a complete census of Milky Way H2 regions, but you notice that there's a big gap of the galaxy here in the third and fourth galactic quadrants where there are no magenta points. This is, of course, the part of the Milky Way that you can't see from the northern hemisphere. So that prompted that motivated the Southern H2 Region Discovery Survey, which was a large project on the Australia Telescope Compact Array that I led. We observed for about 900 hours, doing the exact same experiment. We looked at a bunch of infrared identified H2 region candidates, and we looked for the radio recombination line emission just to prove that they're bona fide H2 regions. The ATCA is an interferometer. It's not as sensitive as the Green Bank telescope. It doesn't have quite the collecting area, but you make up for that a little bit because it has an ultra wideband receiver. It's called the CX band receiver. It goes from 4 to 10 gigahertz. And with the correlator, you get 4 gigahertz of instantaneous bandwidth, which allowed us to observe 20 radio recombination lines simultaneously. So by averaging all 20 of those lines, you could bump up the sensitivity a little bit. It still doesn't get anywhere near the sensitivity that we had with the GBT, but it's better than nothing. So this was another greatly successful experiment. We discovered more than 400 new H2 regions. Here showing the longitude velocity diagram. These are the nebulae in green in the southern sky. And now you really have filled in this diagram completely. In the paper that we just published last month, we do some estimates of the completeness of our galaxy-wide surveys, and it seems that we finally have a flux-limited sample of Milky Way H2 regions across the entire galaxy. So now we get to start doing the really fun stuff, which is looking for galactic structure and galactic chemical structure in these data, which I've talked about at several talks over the past few years. And so I thought today I would talk about some new and kind of interesting stuff. This is a little unrelated to my interests in galactic structure, but it's interesting, I think, nonetheless. So as part of the SHRDS, since it was an interferometric survey, we were able to make images of our H2 regions. And we serendipitously discovered what appears to be a large population of H2 regions with ionized gas velocity gradients. So here, this on the left, this is an image of one of our newly discovered H2 regions from the SHRDS. And the color here is showing the radio recombination line velocity. So we average all of the radio recombination lines together to improve our sensitivity. And then we make this map. This is like a moment one map showing the line velocity across the nebula. And there's a very, very clear gradient of about 10 kilometers per second. Here on the right, the top right panel here is showing the uncertainty in that line velocity, which is quite small compared to the gradient. On the bottom here, this is the radio recombination line full width at half max line width. So this is like a moment two map. And we see some interesting structure there as well. It appears to be have a centrally peaked distribution. That is to say that the line width at the center of the nebula is broader than at the edges by about 5 kilometers per second or so, which again is much larger than the uncertainty shown here in the bottom right panel. This is interesting. It's kind of unexpected. And the only reason that we were able to do this was because we had the sensitivity from looking at all of these radio recombination lines simultaneously, and also because we were using an interferometer. And so we can make these maps. With our previous GBT and Arecibo data, we of course would never have been able to discover something like this. So we were prompted, this is interesting. We were prompted to go back and look at some archival data. Has anybody seen this before? There was some evidence that, people have seen gradients in compact H2 regions that appear to be associated with bipolar outflows or an expanding H2 region. There's some evidence for rotation in a few classical H2 regions, but in the case of the SHRDS, we discovered them in dozens of nebulae, and based off some sensitivity arguments, it seems likely that there's ionized gas velocity gradients in all or most of the SHRDS H2 regions. We had a previous experiment with the VLA, completely unrelated. We were trying to get really accurate electron temperatures to do some galactic chemical structure analysis. But that's also an interferometer. So we went back and looked at those data and analyzed them in the same way just to see if we missed these gradients in those data. And sure enough, in several of the VLA sources that we observed in this other project, there were also velocity gradients. And so this isn't some instrumental thing that has to do with this telescope. This appears to be, a real signal in most, if not all, galactic H2 regions. So here, the center panel now is showing the radio recombination line velocity and the line width on the bottom for this VLA source. So what's going on here? Well, we, considered a couple different explanations. You could have, for example, a bipolar outflow associated with the high mass star at the center of the H2 region. And we did a little bit of simulations and some modeling, and it seemed likely that that was not the source of these gradients. The problem here is that unless you have a humongous opening angle in your bipolar outflow, unless your outflow, is opening up at 50 or 60 degrees opening angle, you can't see it in these data because the angular resolution isn't good enough. Your outflow gets beam diluted and you completely wash out the gradient that you would expect to see from the outflow. And so the other really simple explanation is rotation. Imagine that your ionized gas volume is rotating as a solid body. That's a pretty easy thing to model. So here on the right now, this is a simulation of an observation of an H2 region whose ionized gas is rotating as a solid body. On the top here, this is the line center velocity again, and on the bottom is the full at the half max line width. And so if you have a solid, an H2 region rotating as a solid body, it makes a very clear gradient signature, as you can see here. And interestingly, you can reproduce the centrally peaked line width distribution. And so I think based off of this evidence that we're going to hopefully publish in the next month or so, it seems likely that most H2 regions are rotating, which maybe isn't too surprising. You have to conserve angular momentum somehow. So if the giant molecular cloud that is creating that these H2 regions are being created within has some net angular momentum, that has to transfer down somehow, has to be conserved somehow. And there's actually this problem called the angular momentum problem, where it's a little uncertain how the angular momentum from stars is inherited from the angular momentum of the progenitor galactic giant molecular clouds. And so this discovery here might actually be a way that we can solve this problem. Maybe we have found this missing intermediate step of angular momentum transfer from the large scales to the small scales. Unfortunately, it's really difficult to kind of disentangle the different, or distinguish between the different models in these data. So if you have an outflow or a rotation, you can even try differential rotation, for example. We just don't have the angular resolution that we need to kind of choose between these models. And so last year we proposed for a follow-up survey that I'm leading using the Australia Telescope Compact Array and a more extended antenna configuration to get much better angular resolution observations of the radio recombination lines towards a few of these HII regions. Here are some extremely preliminary results. We just got some data a couple weeks ago. I quickly reduced an image. This isn't all of the data yet, so these images will be even more sensitive. But I just wanted to show what we're looking towards in the future here. So here's a map of an HII region. This is showing the radio recombination line center velocity on the left, and on the right is the line width again. Now with much better angular resolution. So here's our beam down here in the corner. And so now we can really map out the structure across the galaxy, or across the nebula. So in this case, there remains a clear gradient and the centrally peaked line width distribution with some interesting structure in here. And so the next step in this project will be to model these in much more detail to see if we can actually figure out what's going on. What is the source of the velocity gradient? Is it rotation, or is it outflows, or is it a mixture of the both, or is it something else that we haven't even considered? So if you have any ideas, let me know. This is kind of an interesting little problem here. So for the last couple of minutes of my talk, I wanted to switch gears back to something that's more related to my broad research interests, which is structure in the Milky Way galaxy, to talk about what can we do now that we have what appears to be a flux limited census of Milky Way HII regions. So something near and dear to my heart is trying to understand galactic morphological structure using these data, which people have tried to do in the past, and it's quite a difficult problem. So one way that people typically approach this question is by looking at a face-on distribution of stuff in the Milky Way. So a face-on distribution of gas or star-forming regions, or whatever your tracer is. Of course, to make a face-on view of the Milky Way, you need to have distances somehow. And as I mentioned earlier in my talk, getting the distances to Milky Way HII regions is difficult. You can get parallax distances. Mark Reed's done some outstanding work as part of the Bessel survey, mapping out the spiral structure of the Milky Way using high mass star forming regions that have maser parallax measurements. But unfortunately, for most of the Milky Way HII regions, there isn't any maser emission, and so you won't be able to do that for most galactic HII regions. And so I thought, well, why don't we approach this problem a little bit differently? Why don't we approach it in longitude velocity space? These are the two measurables. These are the two things that we observe when we discover and characterize an HII region. So can we approach this problem in LV space directly? And so the idea here is to try to take our longitude velocity distribution of HII regions and fit it to some modeled longitude velocity distribution of HII regions. Here on the right, this is a really simplistic logarithmic spiral, four-arm logarithmic spiral model, just as an example of a kind of model that you might want to fit to the data. So how do we do this? How do we approach this problem, explicitly? Well, if you want to fit a model to some data, you have to be able to write down what's called the likelihood function. This is an equation. This is an expression that tells you what's the likelihood that your data are drawn from the model. So here on the left is a really simplistic example where you're trying to fit a straight line to some data here. And your likelihood function is basically telling you the distance between your data points and the model prediction of the red line here. So if you have some uncertainty in your data, you might want to know what's the distance between that point and the red line relative to the uncertainty. If you've got uncertainty in both the X and the Y direction in this simplistic case, you might want to do something called orthogonal distance regression, which is to try to minimize the distance between the actual distance between the data point and the red line, and something like that. And in the case of this simple model, where it's just a straight line, you're just fitting some straight line to some data, you can write down an equation. You can write down an analytic expression for this likelihood function, basically a least squares equation. But in the case of a longitude velocity distribution with a really complicated model like a logarithmic spiral, it's impossible to write down an analytic expression for the distance between a point and a logarithmic spiral projected into this projected into this plane. It's impossible. And so for a long time, I thought that doing this would be computationally expensive. You have to have some analytic approximation for your likelihood function. It'd be really expensive to compute. And I thought that all hope was lost trying to do this in longitude velocity space. And then I discovered this really interesting tool called simulation-based inference. This is a machine learning algorithm where you train a neural network to learn the relationship between your data and your model parameters. The idea here is that if you can simulate data, if you can have a model of your galactic morphological structure, like a logarithmic spiral model, and you can simulate data from that model, then the neural network can learn the relationship between those simulated data and the model parameters, the pitch angle of your spirals, the orientation of the spirals, and so on. And then, since the neural network knows this relationship, it can give you the likelihood for some new observation. You say, okay, now that you've learned this relationship, what's the likelihood that this actual H2 region was drawn from this model? And it can tell you that number, which is exactly the missing puzzle piece of this problem beforehand. So here's an example of what this simulation-based inference can do. So this left panel here is a longitude velocity diagram showing a simulated single logarithmic spiral arm galaxy. So this galaxy has one logarithmic spiral arm with some pitch angle and a bunch of other model parameters. And then theta naught here is kind of the viewing angle of the spiral. And then the points here are colored by galactic latitude. So this model includes a warp. So this is a simulated data set. It's really cheap and easy to simulate an observation of the model. The second panel here is what the neural network thinks that longitude velocity diagram would look like given that model parameter. So this is what the neural network has learned about the galaxy after running this simulation-based inference. And you can see that's quite the agreement. The neural network has reproduced the observed distribution, the observed longitude velocity distribution for this really simple model. Another way to look at it is this third panel. This is the likelihood function. So this is the true likelihood function. So this is basically what's the likelihood that you'll find an H2 region and different parts of the galaxy given this model. Here, this is the true likelihood function, which I calculated numerically, and it was really expensive to calculate. It took forever, and you can see there's some numerical artifacts here, some glitches. But this is just a demonstration to show that then the neural network learned likelihood function here on the right panel reproduces the true likelihood function quite well. This is a logarithmic scale, and just to highlight that the neural network does put a little bit of likelihood power out here and forbidden parts of the diagram. But if you just look at where the peak likelihood is, it reproduces the true likelihood function almost perfectly. It's actually quite remarkable how well this neural network has learned this relationship with this complicated model. And just to demonstrate that I'm not picking one model parameter that worked, here is an animation where we're cycling through this one model parameter, which is the viewing angle of this single logarithmic spiral, showing those same four panels and how the neural network has really learned this relationship independent of the model parameters. Basically, now the neural network, you can give the neural network any model parameters that you want, and this is a complicated model with 12 free parameters, and it will give you your likelihood function directly. And so now that we have this likelihood function, we can start using some sophisticated analysis techniques like Bayesian Monte Carlo Markov chains to do some inference. Can we fit, for example, a logarithmic spiral model to the galaxy's distribution of H2 regions, or 2 spiral arms, 4 spiral arms, maybe 0 spiral arms, and just have an exponential disk of H2 regions? And we can actually quantitatively compare these different models. We can make predictions, or we can actually assign probabilities that these different models are able to reproduce the distribution of H2 regions, which I think will be the first time that this has been possible to do in longitude velocity space. So stay tuned for that. I'm really excited about this project and to see where it goes. So that's it. Let me just conclude by saying H2 regions are awesome. They're really great tracers of galactic structure. And by constraining the structure of the Milky Way, hopefully we'll be able to learn something about the Milky Way's evolution and formation. Over the past decade or so, we've more than doubled the number of known H2 regions in the galaxy as part of the H2 region discovery surveys and the Southern H2 region discovery survey. And I showed that the SHRDS serendipitously discovered this apparently new population of rotating H2 regions, or at least they appear to be rotating. And hopefully with the new higher angular resolution data, we'll be able to constrain this even more. And then lastly, I showed this kind of new technique, simulation-based inference, that we hopefully will be able to use to finally, once and for all, constrain spiral structure of the Milky Way using galactic H2 regions. Thank you so much for your time.
Thank you, Trey. And I would like to welcome people to put their questions into the Q&A. If you want to ask your questions verbally, you can raise your hand and we can have our moderator unmute you. I had a quick question, Trey, though. In terms of the ones that you see rotation, do you have like multiple H2 regions within a similar complex, and is the rotation correlated from like a large structure, or have you looked into that?
Yeah, that's a great idea. I was just thinking about this the other day, and that's something we should certainly do. I was thinking you could also correlate it with the orientation of giant molecular clouds. There's some studies that have shown that GMCs might be rotating along their their major axis.
Okay.
So it'd be interesting to correlate the orientation of the gradients in the H2 regions with the orientation of GMCs to see if there's any correlation. Yeah, that's an interesting avenue of pursuit. Thanks, Dave.
Okay. Okay, we have a couple questions that came in here. Could you comment on the completeness of the H2 region surveys?
Yeah, so in this paper that we just published last month for the SHRDS, we do some back of the envelope calculations to try to estimate the completeness of our surveys. And at about 10 gigahertz, I think we're complete to a continuum flux of like 200 millijanskeys or so, which corresponds to like a low mass O star at a distance of 5 or 10 kiloparsecs. I can't remember off the top of my head. And so that's the idea of our completeness. It seems like we're mostly complete across the Milky Way for all O star H2 regions. Maybe not out quite to the complete edge of the galaxy, but most of the galaxy.
Okay. And another question, whoops, they're popping in. How large are the possible rotating H2 regions? How large are these regions that are rotating?
Yeah, that's a good question. And so, we characterize in this paper that we're about to publish about these rotating H2 regions, we characterize their gradients in terms of gradients on the sky. So a velocity gradient per angle, because we don't have distances to most of these nebulae. So the next thing we like to do is to get distances to them somehow. Kinematic distances, parallax distances preferably, but kinematic distances if we can. And so that's another project that I'm working on right now, is to try to get distances here. Then we'll be able to see, we'll be able to measure the size of the H2 regions and characterize these gradients in a physical sense. That'll be more illuminating, I think, to understand, the source of the gradient. Okay.
And then there's another question. Any correlation of the metallicity with the rotational parameters?
That's interesting.
Yeah.
I haven't thought about that. Something certainly to look into. I mean, one reason that a population of rotating H2 regions is interesting is that if you have a single dish observation of an H2 region where you aren't able to spatially resolve it, this rotation is going to appear as a broadening of the line width. Since you're just going to have a single pixel on the sky, you're going to see a broader recombination line because of the bulk motions of the gas, which is going to complicate your interpretation of the physical conditions like the electron temperature and the metallicity. And so, an interesting idea. No, I'll have to look for correlations between metallicity and the rotation. Thank you for the suggestion.
And then another question, a comment, they're saying,
oh, Dave froze. I see Mike's comment here. Can we overlay known positions of O and B stars, if any are, over the high resolution data to see if small scale full width max structure are correlated with newborn stars? Hey, that's a fantastic idea. I think you'll be able to do that with a lot of the nearby H2 regions where you can see the OB stars. The problem with that is that the nearby H2 regions are big. They're big on the sky, and so there's typically quite a few OB stars there. And so, yeah, this is an interesting idea. Thank you for the suggestion. We will certainly pursue this.
That was from Michael Bush.
Yeah.
Okay. I think we hit all the open questions that we have now. If anybody else wants to put in a question, feel free to do so. And also, if you want to just comment or ask a question, you can raise your hand. In total, there were about 51 participants during that I saw during the talk, Trey. So fairly good attendance. Okay. Oh, No,
Good
I'm
luck on the
not
job
sure.
search. Thank you.
Yeah, okay, you're seeing the QA. Yeah. Yeah, speaking of which, in terms of capabilities, he's helped with our GBT gritter in terms of software skills. So he's helped our software people here to help optimize our gritter software for our mapping software. Another question came in about a correlation with magnetic fields. Do you see any correlation with magnetic fields?
Yeah, haven't really looked for a correlation with magnetic fields. It's hard to measure the magnetic field strength in these nebulae. There's some ways that you can do it with recombination lines. Technically, recombination lines are sensitive to the Zeeman effect. And so if you had a really sensitive observation of the recombination lines with high spectral resolution, maybe you could at least get a measurement of the magnetic field strength that way. But we haven't done that yet.
Well, since you do have all these H2 regions and you have the model to do like the galactic structure, how big's our galaxy or whatever? Have you do you have any additional constraints on like the size of the galaxy or like itself?
I don't want to make any big claims yet, since the project's still ongoing.
Okay.
Probably they've got it right.
Okay. Any final questions? Anybody want to jump in here or chat and put in your questions? I think looks like we're winding down. So I'd like to thank you, Trey, for coming in and sharing your research. These are great results. It's very interesting. I found, well, anyway, what you're doing with the computational modeling. And I'd like to thank everybody for joining us and hope to see you guys at future community talk days. So thank you very much.
Bye-bye.